Hello everyone, I hope you're all doing well. So in today's video, we'll go through the 2017 Physics Exam Part 1, where we'll be going through question 1 till 10. And yeah, like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. 3 charges are arranged in a line as shown in the figure. Draw an arrow at point X to show the direction of the resultant electrical field at X. If the resultant electrical field is 0, write the letter N at X. Okay, so we have negative, positive, and negative. And this is point X. Let's just draw a basic field line. Like, you know, what's going to happen? Well, I know that field lines go from positive to negative. So this one's going to go like this, and it's going to pass nicely through X, okay? This one, I mean, you should know that the actual resultant is just to the left by just drawing that straight line. We also can have an arrow going to the right in terms of this one, because remember this is positive and it goes to this negative. And so we can also get like a field line where if we were drawing a nice field line like this here, just to draw a nice, show you how it looks. This is how you would draw a field line. Oops. There we go. Oh, it's ugly, but something like this. Wow, it's really pain. There we go. So we draw field lines like these. We can represent them like this. This is a nice representation of how they would look. Come on. All right, something like this. And where the arrows are going from the positive to negatives. For example, this one's going to go this way. This one's going to go this way. This one, where the negative takes it all in, that charge. So like that. Whereas this one's going to go this way. And perfect. I think that's all you're going to need to know. I know I'm going into detail, but overall, at point X, what is the resultant electrical field at X? As we can see, it's to the left. So at point X, we'll rub this whole thing. I just want to show you how the electrical field will look like. Just to the left, pretty much. You just want to draw a basic arrow to the left. That should be your resultant. Easy. Nice. Question 2. According to one model of the atom, the electron in the ground state of a hydrogen atom moves around a stationary proton in a circular orbit with radius 53 picometers, which is this much. Show that the magnitude of the force acting between the proton and the electron at this separation is equal to this. Take K as this, and the magnitude of the electron and proton charges to be this. And show all steps of your working. Alright, let's just draw a basic diagram of how this looks. So imagine we have a little... Think of it as a planet, but it's a proton in the middle. It's the center. It's just a basic proton. So let's draw a proton. A P, and it's a positive proton. And around it, let me actually draw another color. We have an electron. Let's draw a nice circle like that. And so around it, if I just do this, I'm going to rub this part out like that. We have a nice... like electron, so a negative electron, and it's orbiting around this proton. And we know that the radius between the two centers, so from here to here, is this much, which was stated to be 53 picometers. And pretty much, yeah, that's it. And we also have the charges. And what we want to do is we want to show the forces between, so the force acting between the proton and the electron at the separation. Of course, we're going to, of course, get a force that the proton exerts. A force that the proton exerts, and also a force that the electron exerts. And so, and they will be equal, by the way. Those two forces will be equal. And it's quite easy to find that. You should know that force, to find that force, is just equal to K times Q1 times Q2 divided by R squared, your radius squared. So we know our K value, we're saying, is 9.0 times 10 to the power of 9. And we're multiplying it by the charge Q1, which in this case is any. So electron or proton will put, they both have the charge of 1.6 times 10 to the negative 19. So we're just going to write those two. All right. So 2 times. That's it. And their separation squared. So R squared, which we found out it was, make sure it's in meters, so 53 times 10 to the negative 12 meters squared. And that's it. So put that in your calculator, and we should get 8.2 times 10 to the negative 8. Let's have a try at that. 9.0 times 10 to the power of 9. Plus 6 times 10 to the negative 19. Yep. All divided by 53 times 10 to the negative 12 squared. And that gives me 8.2. Yep, times 10 to the negative 8. Beautiful. And so we can write that down. Where the force is 8.2 times 10 to the power of negative 8 newtons. And that's it. So the two forces of these two over here are going to be that over here. Nice and easy. We've showed that. Using 8.2 times 10 to the negative 8 as the value of the magnitude of the force given in part A, calculate the speed of the electron in its circular path. Take the mass of the electron to be this, show all you're working out. Easy. So, this is just circular function. So think of it as circular, like a circular function. So, of course, our speed is going to be perpendicular. So, not perpendicular, my apologies, but tangential to the path. This is your velocity. And so you should straight away know, having a look at your formula sheet. So using our force equation. So which one's that? I'm having a look here. Yes, I've got it. So I know that the net force, having a look at my summary sheet, that F net is equal to mv squared over r. Now, our F net in this case is our actual force, because remember, it's the only force that's acting. And yeah, it's in terms of like the electron, so rub this one out. But the electron, yeah, it's being attracted by the proton, and it's actually that force that it is, yeah. So that's our F net, and that's the only force that is being produced. So that's our F net. And so we got that. And so our F net is, writing it down here, our F net would be, like we said, 8.2 times 10 to the negative 8. Done, newtons. So, and of course, so let's put that all together. So 8.2 times 10 to the negative 8 is equal to the mass of the electron, 9.1 times 10 to the negative 31. Velocity squared, which is what we're trying to find, and the radius, which is 53 times 10 to the negative 12. Which shows that our, putting the square root here, let's do it in my calculator. So 8.2 times 10 to the negative 8, we multiply by that 53 times 10 to the negative 12. And then we divide that value by 9.1 times 10 to the negative 31. And we get this, and we take the square root of that. So 4.77 times 10 to the power of 12, which gives us a velocity. Wow, it's a big velocity, but we wanted to two significant figures. We've used everything to two significant figures. So it's actually just 2.2 times 10 to the power of what? 1, 2, 3, 4, 5, 6. So, yep, 1, 2. Let me do it again. 1, 2, 3, 4, 5, 6. Yep. So to the power of 6 meters per second. Easy. Question 3. Figure 2 shows a schematic diagram of a simple DC motor. It consists of two magnets, a single 9-volt DC power supply, a split ring commutator, and a rectangular coil of wire consisting of 10 loops. The total resistance of the coil of wire is 6 ohms. The length of the side JK is 12 centimeters, and the length of KL is 6 centimeters. Okay. The strength of the magnetic field is 0.5. Okay. Determine the size and the direction of like AF of the force acting on JK. Let's have a look. So on the force JK, we're actually gonna be attaining a force because it is perpendicular. So this is where we're going to get current, by the way, because remember, this is your positive, and so current's going to start going this way, moving this way, going to go past that way. So it's going to be, on JK, it's going to be passing straight like that. And the magnetic field lines are going to pass perpendicular to it. Remember, this is north to south. They always pass from north to south. So imagine this is being producing, let me draw it nicely here. This will produce a field line that will go like that. As you can see, they are perpendicular. And using your right-hand slap rule, make sure you put your thumb in the direction of the current and your fingers to the direction of the magnetic field, and see what your palm, and your palm pretty much shows the direction of the force. So doing that, I can straight away see that the force is downwards. So there, the force will be downwards. Meaning that this point over here, also this point, is going to have to be upwards. So our actual thing is going to be rotating this way. It will rotate anti-clockwise. Easy. Now the question says, determine the size and the direction AF of the force acting on JK. Like we said, JK is actually acting downwards, so it will be D. So we can put D in here. Direction is D. Now let's just try to calculate the force. Now we know to calculate the force for these questions, it's equal to N length times your current and your magnetic field strength, where our N is the number of loops, which in this case was 10 loops. Your length of the wire JK, which was said 12 centimeters, so change it to meters, so 12 times 10 to the negative 2. The current. Now to get the current, we're not actually given the current, but remember, we're given the resistance and the voltage. By Ohm's law, we know by Ohm's law here. Let me just draw straight lines. By Ohm's law, we know Ohm's law states that voltage is equal to I times R, your resistance. So if we want the current, which in this case would be, voltage over R, it's just going to be, what's your voltage? We said was 9 volts, yep. So it's going to be 9 divided by your resistance, which is 6 ohms, which gives us 9 divided by 6, and that gives us 1.5 amps. So put that there. And times your magnetic field strength, which is B, which is 0.5. Putting that all in our calculator, we get what? Something 2, 1.5, and 0.5. That gives me 0.9 newtons. To how many significant figures? We need it all to 2 because everything that we've used was 2 significant figures. So we write it as 0.90 newtons. Remember, we don't count the 0 as a significant figures, so we have to put an extra 0. So these are 2 significant figures. Nice. B. What is the size of the force acting on the side KL in the orientation shown in figure 2? Explain your answer. Let's have a look. KL. So KL, let me just rub this part out. I want to rub this out so I can have a look at this. So KL is this one over here. And of course the current's going to go this way. See, the problem with KL is actually the force, it won't even have a force. It's because it runs perpendicular to the magnetic field. The current direction, as we said, runs perpendicular to the magnetic field. And what do we know about that? The force, there will be no force produced. Because remember, the current has to be perpendicular. But here, sorry, what am I saying? Let me reiterate pretty much. If the current and the magnetic field are parallel, the force will be 0. They must be perpendicular to produce a force. In this case, as we can see, they are parallel. So there would be no force. So straight away, easy mark. KL, there is no force produced. So we can put 0 here, newtons, and we need to expand because it's 2 marks. All you have to say, just one dot point, the direction, so the direction of current is parallel. Oops. So it's parallel to the magnetic field. And pretty much hence 0. Hence no force will be produced. Hence no force will be produced. Easy. Nice and done. So the direction of current is parallel to the magnetic field. And yeah, pretty much that's it. Next question. Question 4. Charon, a moon of Pluto, has a circular orbit. So I would like to always draw a diagram to represent this. So imagine we have something like Pluto over here. So this part here is, let's call it, yeah, the green is just Pluto. So this is Pluto, and of course it's going to have an orbit. Oops, that's not the most nicest, but we can put it nicer like this, and let me move it outwards. There we go, something like that. So this is Pluto's in the middle, and so we know that Charon is a moon at the Pluto, and it's orbiting. So we can just rub some part out like this. Let me just rub this part out. And just draw another color, and let's just call this over here Charon. So that is Charon, and the radius of orbit, we're given the universal gravitational, we're also given the radius of Pluto and everything, the mass of Pluto. Beautiful. Let's see this. Assume that Pluto is a uniform sphere. Calculate the gravitational field strength at the surface of Pluto shown in your working. So show your working out and include the appropriate units. Easy. So what we want to do is we want to calculate the gravitational field strength at the surface. So what are we going to need? We're going to need this over here. This is the radius, and of course the radius is on the surface of Pluto, and that's it. We have our radius. This is our R value. It's just our radius. And of course, we have the mass of Pluto, which is creating that gravitational field. And yeah, that's all we're going to pretty much need. So we know that G, your gravitational field strength, it's just equal to G M over R squared. So where your G, in this case, is, your gravitational constant, which is 6.67 times 10 to the negative 11. M is the mass of Pluto. It's the one that's creating that gravitational field. So 1.3 times 10 to the power of 22, and the radius of Pluto, which in this case is 1.2 times 10 to the power of 6 squared. So putting that in our calculator, 6.67 times 10 to the negative 11, 1.3 times 10 to the power of 22, 1.2 times 10 to the power of 6, all being squared. Have I made any mistake in my calculations here? Let's check. 1.3 times 10 to the power 3. Beautiful. And we're given that it's approximately 0.60. Now, how many significant figures? Well, the lowest is 2, so it's going to be just 0.60. So 0.60, and we have to also write the units. There's 2 units for gravitational field strength. It's the same as acceleration. We can write it as meters per second squared, or we can write it as what else? So we know that force is equal to mass times acceleration, and so we can write it as Newton per kilogram. Newton per kilogram. And that's it. We can also write it like that. Any way you write it still gives you the same answer. Anyway, you would still get full marks. Next question. Calculate the period of orbit of Charon shown in your working out. I don't know if I'm saying it wrong, but I believe I am. But, who cares at the end of the day? So let's have a look at this. So we want to find the period of orbit. So we're going to actually need the radius of orbit, which in this case would be this. It's the center to the center. Right over here. That's what we're going to need. And we're actually given that. It's right over here. We're given that the radius of orbit of Charon is this. So all we're going to need actually is using your Kepler's law, which is over here. So r to the power of 3 divided by t squared, which is your period, and that's what we want to calculate, is equal to 4 pi squared. And so I think kind of reciprocating everything. So imagine put these upwards. So twist them. So it'll be just t squared over r to the power 3, 4 pi squared over gm. Multiply both sides by r to the power 3. So we just get t squared is equal to 4 pi squared r to the power 3, all divided by gm. And so take the square root of both sides, we would get, the square root of that. And that's our formula to find the period. Easy. So let's put that there. So your period is just the square root of 4 pi squared. Your radius of orbit, which we said, which is 1.8 times 10 to the power of 7 to the power of 3, all being divided by g, which is 6.67 times 10 to the negative 11. Is that right? Times the mass. And this is the central mass. What is orbiting the central mass, which is Pluto? Always, the big M means the central mass, which in this case is Pluto, which is 1.3. 1.3 times 10 to the power of 1.3 times 10 to the power of 22. Have I made any mistake in our calculations? Great, looks all good. Subbing every value, and now let's calculate what that is. So square root, so 4 times pi squared times 1.8 times 10 to the power 7 squared. So to the power 3 actually. Yep, so 1.8 times 10 to the power 7, 3. It's equal to 0.67 times 10 to the negative 11. All right. 1.3 times 10 to the power of 22. All right, that looks good. And so we get our period, which is to how many significant figures? Everything pretty much by 2. The lowest is 5.2. So 5.2 times 10 to the power of what? 1, 2, 3, 4, 5. 5, is that right? 1, 2, 3, 4, 5. Great. 5.2 times 10 to the power of 5 seconds. Done. Question C. Scientists wish to place a spacecraft of mass 1,000 kilograms in an orbit of the same radius as Charon. 3 students, Rick, Melissa, and Nam, are discussing the situation and have different opinions. Rick says, as the spacecraft is lighter, it will have to move at a greater speed than Charon to achieve the same orbit. Melissa says that the spacecraft would need to move at the same speed as Charon, and Nam says that the spacecraft would need to only move at a lower speed as it's lighter than Charon. Evaluate these 3 opinions. Detailed calculations are not necessary. Alright, so what do I always tell students? This is always important. Your satellite mass, remember there's 2 masses always in these calculations. We get the mass of the central, this over here, this is your mass of the central mass, which is the main mass that it orbits, and we have something called satellite mass, or, in terms of this, it's the actual spacecraft. Imagine this over here is your spacecraft. Now, forget about if it's not Charon anymore, so it still has the same radius, of course, so it's still the same radius, but now it's actually a spacecraft. And it's less, it weighs less, of course. The main thing so let's actually evaluate this. Rick says that as the spacecraft is lighter, it will have to move at a greater speed than Charon to achieve the same output. Rick is wrong, 100% wrong, and here's why. Remember that the mass of spacecraft is independent on the speed. Remember using your formula, so using your formula over here, the speed. To find the speed, remember its velocity is equal to the square root of g m, which is your central mass, over r. What it tells us is that your velocity is only dependent on the mass of the central mass, which is, the Pluto, not the spacecraft. So even the spacecraft could be like so much heavier. If it's in that same radius, if it's the same radius as Charon, it will move at the same velocity. That's what it means. It doesn't, so your mass, the mass of a spacecraft is independent on the velocity. You can have a bigger spacecraft, it wouldn't do any change if you put it in the same radius as Charon, or you can have a little teeny weeny one and it will still have the same velocity. It doesn't matter. That's what it's telling us, this formula. And it's very important to know that over here. So Rick is saying, let's evaluate it together. Rick says that the spacecraft is lighter. So as the spacecraft is lighter, it will have to move at a greater speed. Rubbish. It will move at pretty much the same speed, because it will be at the same radius. Remember, it will move at the same radius as Charon. So nope, to achieve the same orbit. Yeah. So Rick is wrong. Remember, even though the spacecraft is lighter, it doesn't affect the velocity. That's the main here. What about Melissa? Melissa says the spacecraft would need to move at the same speed as Charon. Pretty much true, because if she moves at the same speed, imagine she moves at the same speed as Charon, it would, remember this mass is constant, it's actually the mass of Pluto. It means this radius has to be the same radius as Charon, which is great. That's what we want to aim for. And so Melissa's not wrong. It's true. So using your formula, that's absolutely true. So Melissa will give her a nice tick here. Nam says that the spacecraft would need to only move at a lower speed as it's lighter than Charon. Again, even though it's lighter than Charon, it will, you remember, your mass of your satellite or your mass of your spacecraft is independent to the velocity. All you need to do, if you still put it in the same orbit, the same radius, it will move at the same velocity. Or if you put it at the same velocity, it will move at the same radius. It's independent. So Nam is also wrong. And yeah, so what we're just going to do is evaluate these here. Let's put some, So let's try to write some stuff. What I'm going to write is, okay, let's evaluate first Rick. So so we can say that Rick is incorrect. The speed. So what we're doing is evaluating each. So the speed required to maintain a stable orbit depends only on the on the mass. So on the mass of the central body and the radius of orbit. So only on the mass of the central body, mass of the central body, which is in this case Pluto. So that's that. And the radius of orbit. The radius of orbit. Yep, and we want to also show the formula that we understood the concept from. So velocity is equal to the square root of GMR squared. So GMR, sorry. Is that right? Let me have a look at my phone shit. Velocity, yep, GMR. Beautiful. So we've got that. And so the mass, wrong color. So the mass of the spacecraft doesn't affect the orbital speed. That's it. So this here, we've kind of very detailed answered why Rick is wrong. So let's also do Melissa. Melissa is 100% correct. Melissa, let me spell her name right. Melissa is correct. So both, we can say both Charon and the spacecraft. So the spacecraft would, so it would need to move at the same speed to maintain a stable orbit. A stable orbit at the same radius. So same radius around Pluto. Beautiful. And last and lucky last, we're gonna write about Nam. Why is he wrong? Nam's just pretty much the same thing as Rick, but so we're gonna write Nam is incorrect. Is incorrect. As mentioned earlier. As mentioned earlier, the mass of the spacecraft is independent on the speed required for orbit. It's primarily determined by the mass of the central body and the radius of orbit. Wow, my hands hurts, man. That should be very detailed, and yeah, I think that should give you, and that's in conclusion, Melissa's correct, and that's it. I think that if you've evaluated those very specifically, it should give you full marks there. Question 5. The altimeter in figure 3 has a rectangular coils with sides 0.3 millimeters and 0.40 meters and 10 turns. The coil rotates 4 times a second. This is key. So if it rotates 4 times a second, this is your frequency. Remember, what is frequency? What's the definition on frequency? Frequency is the number of cycles per second. So if it rotates 4 times a second, that's your frequency. That's the definition of frequency. So we know how frequent. Let's So we know our frequency in this case, just by that, is 4 hertz. And so in a uniform magnetic field, the magnetic flux through the coil in position is 0.2 Weblins. Calculate the magnitude of the magnetic field, include an appropriate unit. It's easy. So that's 3 marks. Nice. So we know that magnetic flux, so magnetic flux is equal to the area times your magnetic field. What's our area? Well, it's easy. It's just multiplying these two together, and especially there in meters makes our life much easier. So it's going to be, that's your area, so it's just going to be 0.30 times by 0.40 times your magnetic field, which in this case is just 0.20. And so 0.3 times 0.4 times 0.2, which gives me 0.024. And we've got that, and we use all two significant figures. So let's just write that in our answer. So it's just 0.024 Teslas. Remember, Tesla is the unit for magnetic field. Have I done anything wrong here? So remember, yep, B times the area, and we got our area by multiplying those two. That looks good, and we also multiply by the... No! What am I doing? No. Oh my god, what am I doing? Wow, what have I done? Sorry. I fully forgot. Sorry. We're trying to calculate the magnetic field. So we know that the magnetic flux is equal to your area times your magnetic field. So B is your magnetic field, which is your flux over your area. And we know our flux, they've given it to us, 0.20, all divided by your area. Again, your area is just 0.30 times 0.40. That's it. I don't know what just happened to me. Wow, I just lost it there. So 0.3 times 0.4, and that gives me, yes, okay. And so I wanted two significant figures, which is 1.7 pretty much. 1.7 Teslas. Is that right? Beautiful, looks good. Nice. Question B. Calculate the magnitude of the average EMF, generated in the quarter of a turn. Show all the steps when you're working. So, okay, we know that EMF is just equal to the number of turns. We don't care about that negative. We're just trying to calculate EMF, the magnitude, so don't worry about that. Times your change in magnetic flux divided by your change in time. So, what's your number of turns? Well, how many loops were there? 10 turns, sorry, there's 10 turns. Your magnetic flux was given to us. Okay, so if it's a quarter turn, so if it's initially at this position and if it's quarter turn, there's a big change in flux, and yeah, it would be 0.20. So it's still 0.20. And your change in time. Now your change in time has to be for that quarter. So remember how we got our frequency? We know that frequency to get period is just this reciprocal of frequency, which in this case would be 1/4, which is 0.25. Now that's for, remember, your period is how long does it take to complete one full cycle. Because we're only taking a quarter of that cycle, we have to times it by 1/4, so a quarter. So imagine 0.25 times again by 1/4, and that's going to give us 0.25 times 1/4. That gives us, let me write it here, 0.0625 second. That is your time. So 0.0625 seconds, and putting that all in the answer. So 10, 0.20, and putting that as an answer. That gives me 32 volts. Easy. Nice 32 volts. 3 marks. Wow. Quite nice and easy. I think, yeah, of course, I would put this over here. This is going to be a 1 mark here, right here. So I'm going to just cut it here and put it right over here. There we go. So something like that should give you 1 mark extra. That's it. Easy. Question figure 4 shows the output EMF versus time graph for an alternator for 2 complete cycles. Okay, the 2 slip rings in figure 3 are now replaced with split ring commutator. Aha, a split ring commutator. What do we know about a commutator? Every turn, so every cycle, halfway through it, it's gonna rectify it. So it's gonna reverse it. So for example, have a look over here. We know this is one cycle, so look, that's only one cycle. Halfway through it, this part is going to be rectified. So it's going to be reversed. It's going to be reflected. So what's just going to happen is, whatever, this is the most easiest to do it, is whatever you see these parts over here, just reflect them to the top. So it will look like that, pretty much. And of course, forget about these ones at the bottom. So let's do that there. On the axis provided, sketch the EMF versus time graph of the new arrangement for the 2 complete cycles. Easy. So yep, again, so nice and easy. Wow, it's actually, I want to draw it nice, so like that. I'm pretty much copy and paste these, duplicate them. I want to just duplicate these, and this is how they look. Pretty much, that's how it should look when you use a split ring commutator when you replace slip rings. An easy mark. Done. That's it. Question 6. Let's try this. I love these kind of questions where they have transmissions. Figure 5 shows a generator and an electrical power station that generates 100 megawatts of power at 10 kilovolts AC. Transformer T1 steps the voltage up to 500 kilovolts for transmission through the transmission wires that have a total resistance of 3 ohms. Transformer T1 steps the voltage down to 50 kilovolts at substation. Okay, assume that both transformers are ideal. Remember, ideal means that power is not lost and it's constant throughout. Yeah. So A, the current in the transmission lines is 200. So this is your transmission lines. This part here is your transmission. So we're saying it's 200 amps. Calculate the total electrical power loss in these transmission lines. Easy. We know from the formula, power loss is just equal to your current squared times your resistance. So we know our current that's running through this transmission wire is 200 amps. And so the resistance in those transmission wires are 3. So I'm getting this. So 200 squared times 3. That gives me this big number. And we want it in kilowatts. So we want to just divide it by pretty much 1,000. So it gives us 120 kilowatts. And yeah, that's it. Next question. Transformer T1 stepped up the voltage to 250 kilowatts instead of that 500. So, okay, we're not doing 500 anymore. We're doing, all right, so we're doing 250. So we've halved the voltage. By what factor would the power loss in the transmission lines increase? So wait. So we used a current. When we used a current of 200 amps, the power loss was 120. Let me write that nice. 120 kilowatts of energy that was lost. And so now we've got a different voltage. So imagine forgetting about this 500 here. And now it's 250. Because the power is ideal, think about it. Because the power is ideal, this power is going to be the same in the secondary part of the transformer. So we can write that as just 100 times 10 to the power of 6 watts. So you should know this over here. Make sure that's in kilovolts. We already know that, let me just draw it over here. So we know that power is equal to voltage times current. And now because we have the power on the secondary, which was, oh no, we want to find the current. The main thing is the current to find the power loss, so which is just power over V. And we know that the power, which is on the left side, which was 100 megavolts, will be the same on the right side, which is 100 again megavolts. So it'll be 100 times 10 to the power of 6. All divided by your voltage. Make sure, yep, which in this case is 250 kilovolts. So 250 times 10 to the power of 3. So putting that in your calculator, that's gonna give us 400. The current is 400. It's actually double. So 400 amps. So now using a 400 amps, how much is the power loss? Let's understand that. So we know that the power loss for 400 amps is what? So again, using the formula, P is equal to I squared R. So what's our I, which is 400 squared. The resistance still constant. It's still in the transmission, which is 3 still. Putting that in your formula times 3, we get in terms of what? So 480, right here. So 480 kilowatts, which is what? A factor of 4. So by what factor would the power loss in the transmission lines increase? It will increase by a factor of 4. So 4. Nice. Wow, for 2 marks, that took time actually. Or I think I kind of did the slow method, but yeah, that's how I would have done it. Question 7. Okay, looking at it straight away, I know it's banked, and I love those kind of questions. A bicycle and its rider have a total mass of 100 kilograms and travels around a circular bank track at a radius of 20 meters at a constant speed of 10 meters per second, as shown in figure 6. The track is banked so that there is no sideways friction force applied by the track on the wheels. On the diagram below, draw all the forces on the rider and the bicycle, considered as a single object, as arrows. Draw the net resultant force as a dashed arrow labeled as F net. Easy, so let's draw all those important forces. Of course, what the first force is in the center of mass is the force of gravity. So we're going to draw a straightaway downward force. Let me write it like that. And this first force is the force of gravity. And we're also going to actually get a normal force that's going to be acting on the surface. And it's going to be this way, which is your normal force. And so your F net, where would that F net be? It will be towards the center of the circle over here, which is, in this case, right over here. So putting a dotted lines, F net. And that's it. And very nice typical question in exams. Easy marks to get in. How much marks? 2 marks. Quite easy to get. Calculate the correct angle of bank for there is no sideways friction force applied by the track on the wheels. Show you're working out. Beautiful, easy question. So going to my formula sheet. Whenever you're doing questions when there is banked, this is the formula that you should be using to find the angle. Theta is equal to your tan inverse, alright, V squared over RG. This is only used for banked. And so let's do it. And what's that going to give us? So tan inverse, what's our velocity? They said it was 10 meters per second. So tan squared all divided by your radius. In this case, our radius is 20 meters. And your g value, which is 9.8, acceleration due to gravity, which putting all these together, we should get our angle. And so our angle is going to be 10 squared, 20... 9.8, and so it's 27 degrees. Easy. 27 degrees. Done. Question 8. Let's have a look at this. A roller coaster is arranged so that the normal force on the rider in the car at the top of the circular arc at point P, as shown in figure 7, is briefly 0. So there is no normal force. The section of the track at point P has a radius of 6.4. Okay. Calculate the speed that the car needs to have to achieve a 0 normal force on the rider at point P. So let's first create an equation. Let's actually understand what's happening here. So, of course, we're going to get a force of gravity, yeah? Of course, you know, there's going to be a force of gravity, which is going to be acting downwards. Of course, we're going to get a normal reaction force that will be normally upwards, yeah? Which I'll call N. That's our normal reaction force that will be acting upwards. And we'll get an F net. And where is our F net? Where is our net force? It will always act towards the center of the circle, as we said last time. So imagine our F net is over here in this direction. So this is your F net. So we can actually just make an equation over here. So F net is the sum of these forces. So F net is the sum of these forces, which of course will be Fg minus N. And why do I put on minus N? Because I'm taking down as positive. Remember where the direction of F net is, the net force, we'll take that as positive and hence that. But in this question, we're saying that we achieved 0 normal reaction force. So there's no N value. N is 0. Given that we know N is 0, we're going to just get rid of it. So imagine getting rid of N. Like this. So we only get F net is equal to Fg. And so F net, remember what's our F net formula? So the net force for circle functions, it is mv squared. So mv squared over r, is that right? Is equal to Fg, which is mg. Now, of course, the masses will cancel out. So we'll get v squared over r is equal to g. Hence, v is just the square root of rg. Yep, so Beautiful. And hence your velocity is just going to be, let's put those all together. So what's your radius? Your radius of the is 6.4. Be careful, not this one over here. It's towards the center of the circle and the radius, which is 6.4. So 6.4, g is 9.8, and this is going to give us our answer, our velocity. 9.8. And so it gives me 7.9, blah, blah, blah. But how many significant figures are we dealing with? We're dealing with two significant figures, which is hence 7.9. So 7.9. I want to see, have we done anything wrong here? Looks all good, to be honest. Absolutely good. So it looks all good. So 7.9. Done. B. The car is faulty and only achieves a speed of 400 meters per second at the top of the arc. So, okay. At P. So let's just rub all this. I don't think we're going to need this. Let's just rub this out. All right. So at the top P, it only achieves a 4 meters per second at the top of the point P. Calculate how fast this car would be moving when it reaches the bottom at point Q, which is 5 meters down. So, okay. Below point P, assume that there is no friction and no driving force on the car. Beautiful. You should straight away realize that this is where we're going to use energy conservation. We know that at the top, because there's velocity, they said it was like 10 meters per second, wasn't it? So they said that the car, no, it was moving at 4 meters per second. Because the car here has some velocity at the top of P, we're going to be having some kinetic energy. So we're going to have some kinetic energy here, KE. It's so ugly, I'm so sorry, but we're going to have some kinetic energy, so KE. And we're also going to have GPE, gravitational potential energy, because it's above some height, which is 5 in this case. We're going to take that 5 as this is ground. Over here, this is ground. And so we hit 5 meters. Yep. So we're also going to get kinetic energy and GPE. We're going to get these two. And so as it rolls down, all that gravitational potential energy will be converted to all kinetic energy. So here, it will all be only kinetic energy, because there's no more height at the bottom there. And that's it. This is where we're going to be using energy conservation. We know if we add these two, it should be equal to this kinetic energy at the bottom of the Q, because of energy conservation. So, and that's what we want to do. We want to calculate what is the speed at Q. So again, we're going to write kinetic energy at the top. So kinetic energy plus GPE, this is at the top, is equal to the kinetic energy at the bottom. And so kinetic energy is, half mv squared plus GPE, which is mgh, and kinetic energy was just half mv squared. We can actually get rid of the m, because they all have m, so we're just going to write it as half v squared plus gh is equal to half v squared. And so this is at the top. And what do we know? We know half. What's the velocity at the top? They said it was 4, as they from here. So 4 squared plus g, which is 9.8. And what's the height at the top? As they said, it was 5 meters. And that's all equal to the kinetic energy at the bottom, which is half v squared. So let's just calculate that. So 0.5, 4 squared plus 9.8, 5 times 2. So we're going to get velocity is equal to the square root of 114, which is square root of that. Okay, we get our answer, which I think we wanted two significant figures, which is 11 meters per second. Easy. And that's it, yeah. Looks good. Is that right? We got that. Good. All right. Question 9. Let's have a try at this. Students use a catapult to investigate projectile motion. In the first experiment, a ball of mass 0.1 kilogram is fired from the catapult at an angle 30 degrees to the horizontal. Ignore air resistance. In this first experiment, the ball leaves the catapult at a ground level with a speed of 20 meters per second. Okay. However, instead of reaching the ground, the ball strikes at 26 meters from the launching point, as shown in the figure 8A, and figure 8B shows the enlarged view of the catapult. Beautiful. So they've just put all the information here. Calculate the height of the ball above the ground when it strikes the wall. So we want to calculate this part over here, this height from here to here, this value of height. Easy. Well, what we're going to do is, all right, because we're given the actual range, the horizontal distance, and we already know the horizontal velocity, remember it is constant throughout. So your initial horizontal velocity is the same for all. Yeah, it's always constant. So what we're going to do is we know that distance for, for velocity. So remember distance, in this case, distance is equal to VT. And this is for your, X, like the horizontal thing. And so we know our distance is what? So we said the distance is 26. And we know our velocity is, be careful, so remember, break this down. So we're going to break it to its component, which is going to be, actually this one's much easier because they have the angle. So it's going to be 20 cos, let me write it down. So 20 cos 30 degrees times t, hence time. So the time it takes for the ball to be shot and hit that wall that's what we've just calculated here. So it's going to be 26 divided by 20 cos 30, which is 1.5 seconds. So 1.50 seconds. So it'll take that much time. Now we're going to use our vertical components. So we know initial vertical component is what? That's your initial velocity is going to be 20 sine 30. We know acceleration due to gravity in the vertical direction is negative 9.8. What we're trying to calculate is S, the displacement in the vertical direction, and that's going to give us our height. So, yep. And we also know the time it takes, which was 1.50 seconds. So, what formula should we use here? Of course, this should come in your mind. So, S equals U T plus half A T squared. So, your S is U, which is 20 sine 30 degrees times your time, which is 1.50, plus half negative 9.8 t, which is 1.50 squared. Have I done anything wrong here? All right, so it looks all good. So let's put that all in our formula sheet. So 20 sine 30 times that plus 0.5, so half times negative 9.8 times this squared, and we get 3.96, some distance, and that is our distance, our height. To how many significant figures? I believe 2. Our answers are all in 2, so it's actually 4.0 meters. So it's actually, 4.0 meters, it looks like. Have I done that perfectly? Yep, looks good. Question B. The students next investigate the relationship between various initial variables and range R on the level ground as shown in figure 9. In this experiment, they use a 0.1 kilogram ball and keep the caterpillar at a fixed angle of 30 degrees, degrees during the experiment. The ball lands on the same height as it is fired. Okay. The variables in this experiment can be classified as controlled, dependent, or independent. Complete the following table by providing one variable from the experiment to each classification. All right. So the first one is controlled. Remember, the controlled variable is the variable that is kept constant throughout the experiment. And in this case, they just told us what they are. They told us it's the mass of the ball, and they also told us the angle. So we actually have 2, but I think you only need to put 1 because it's 3 mark 1 in each, they said. In this case, I'm just going to put angle. So angle. Actually, I'm just going to put the mass of the ball, much easier. Mass of ball. That is one of your control variables. Now, dependent. Your dependent variable is the variable that you're trying to measure. It is, for example, think of it as the y-axis. So think of like an equation. Y equals mx plus c. X is your independent variable and y is your dependent variable. We start subbing values of x and it's going to result in y values. And this is what our dependent variable is. And it's it's what we're trying to measure. That's what it is. So in this case, what are we trying to measure? Well, we're trying to measure, in this question, the range. So, So we're saying the students next investigate a relation between various initial variable and the range. They're trying to see what, the range is. So that's your dependent variable. So the range. What about your independent variable? Your independent variable is the thing that you change. And that results in that change in your dependent variable, which is the range. So the thing that they're changing in this case is your initial velocity. So we can say initial velocity. Nice and easy. C. The students gather the following data from a series of experiments similar to the one described in part B. All right. And here we have, so we're given some initial speeds and a range, and I believe they're going to make us graph it. Yes, they are. So the students use a tape measure that is marked with 10 centimeters to measure the range that the ball traveled at different speeds. This is important. This part over here. So imagine you have a ruler. We're going to probably find the uncertainty in this part. So imagine you have a ruler here. Nice basic ruler. And so we have intervals, so imagine these are your intervals. And of course they're telling us, well, it's not the most nicest intervals I've drawn, but this is what the intervals look like. And imagine the intervals are spaced 10 centimeters. Remember that whenever you have something like like a ruler or a voltmeter and ammeter, anything like this, whenever you have some intervals, to find the uncertainty is you take the interval, which in this case is 10 centimeters, and you divide it by 2. In this case, your uncertainty is just 5 centimeters, which is plus or negative. In other words, 5 centimeters just 5 times 10. Make sure it's in meters, make your life easier. So it's just 0.05. Easy, meters. Have a look at this. On the group provided below, graph the data gathered by the students from the table on page 24. Include scales and units on each axis. So we want to include scales and axes. Insert appropriate uncertainty bars for the range. As we said, we have the uncertainties for the range distance on the graph, and draw a smooth curve of best fit, which this is 8 marks. All right. So let's actually do this. First, what we're going to do is we're going to include scales. That's the main important part. Let's have a look at the initial speed. First, of course, make sure the range is going to be measured in meters in this case, and our the initial speed is going to be measured in meters per second. That's important to put that there. That's your units. And now let's put some scales. So first, let's do the initial speed. What are the initial speeds going by? They're going 1, 2, 3, 4. So we're going to do, because they're very spaced out, we're going to do 0.5, 1, 1.5 by 0. We're going to go by each scale into each interval by 0.5. So for example, it's going to be 0. This part here is going to be 0.5. I want to make sure if everything's good. So yeah, I want to make sure it's to 2 significance. So that 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, 0.40, 0.45, and 0.50, and 0.55. Is that the maximum that should be enough? Yeah, that's enough. That's enough. So 5 is the max. What am I doing? What am I doing? So sorry. What? Oh my god. It's supposed to be 1.0. 1.0. This is 1.0. Yeah, duh. I'm so dead tired today. I don't know what's happening to me. Let me just rock these out. All right. 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, 4.5, 5.0, and 5.5. Perfect in meters, done. And what about the scale? So these scales are going by that much. And so that is your range. And the range is 10, 35, 78, 142. And how much? So we got 2, 4, 6, 8, 10. Wow, we have a lot. So we're going to actually just go by 0.5 to be safe. Yeah, this goes by 0.5 meters. So, for example, so each interval is 0.1. So like this is 0.1. So 1, 2, 3, 4, 5. So here is going to be 0.5. Is that right? I want to make sure 0.50. I want to have a look at that. Yeah, that looks good. That looks good. So that's that. So 1, 2, 3, 4, 5. So it's going to be 1.0. 1, 2, 3, 4, 5, which is 1.5. 1, 2, 3, 4, 5. Yep, 1, 2, 3, 4, 5, which is 2.0, and 1, 2, 3, 4, 5. Great. So 2.5. Yes, and the max was 2.15. Great. So we have this beautiful part here, and now let's just plot those points. So the first point was so it was initial speed at the bottom. which is, remember your initial speed is your, because it's at the bottom, it's in the x-intercept, it's your independent variable. Did we also get that? Independent variable? Yes, the initial velocity. So the first point we're going to put is 1 and 0.10. So 1 at 1, 0.10, which is here. So at 1, it's 0.10. Is that right? Good. Next one, 2, 0.35. So at 2, so 1, 2, 3, right in this part here, which is 0.35. Good. Well, next one is 0.78 at 3. So 0.78. So if this is 0.55, 6, 7, approximately over here, that should be 0.78. Yeah, 6, 7. Yes. And so at 4, it's 1.4. So at 4, it's 1.4. So 1, 2, 3, 4, which is right over here. 4 is 1.4. Looks good, yeah. And at 5, it's 2.15. At 5, it's 2.15, which is 1.5 is here. So approximately right over here. Great. And so we got this nice graph. And of course at 0, if you have like zero speed, of course you're not going to get any range. So it's going to start at 0. And so also what we want to do is we want to draw the uncertainty bars. We don't want to forget those. So uncertainty bars is 0.05 in that range. So we're not going to draw one here. This is not included. This is just 0, but it's the other one. So if I know that this part is 0.10, 0.10, it's just going to be halfway. So it'll be these two. That and that. That's going to be the first. That, like that. Something like that, like that. Nice. That and that, like this. And that, like that. Perfect. That looks good. So 0.05, which is just half the distance of that. Done. And now let's just sketch a nice curve. That will pass us through all those uncertainty bars. So a nice curve. Let's try to do that. Let's use a green graph. What the hell? Why is this so hard to... What? It's really... I'm really struggling to use... Yeah, it's a pain. So what I'm going to do is I'm going to just nicely, roughly sketch it. Pass through all these points. Smooth. But, okay, this is hard because it's like you need to get a nice curve into it. What's wrong? I'm really struggling to draw a nice... Alright, it's not passing through all of them. So it must pass through all the uncertainty bars. That's 1, 2, 3, 4, and 5. So now it's passing through all those uncertainty bars. That's it. And I think you only need it from this point here. And that's it. This is a nice graph. Do we have everything? So do we have the graph the data? Yep. Include scales and units. Yep, the scales and units. Insert appropriate uncertainty bars. Looking good. And draw a smooth curve. This is a nice smooth curve. Beautiful. Last question for today. The length of a spaceship is measured to be exactly 1/3 of its rest length. So your actual length, your length contraction is 1/3 of your proper length. That's what they're saying. As it passes by observing station, all right, the length of spaceship measured by exactly 1/3. Yeah, because remember length contraction. Yeah, if it's 1/3 of the length of the proper time, means yeah, this here is your length contraction. What is the speed of this ship? What is the speed of your ship as determined by the observing station, expressed as a multiple of c? Nice and easy. We write this as actually just L0 over 3. Now we know that the formula, length contraction is just your proper length divided by your Lorentz factor. So, if I know that L is equal to this, I can actually sub that L in here. So what I can do is I can just take that out. Let me bring this here. Is I can take this part here and bring it right over there. All right. And we got a nice relationship here. What it's telling me is, of course, like these cancel out. It's telling me like L, your proper length is equal to the top part, of course. So it means your Lorentz factor should be equal to 3. That's important. So your Lorentz factor is equal to 3. And we know our Lorentz factor is what? It's actually just 1 over the square root of 1 minus v squared over c squared. Remember, that's what we want, the v squared. And we know that's equal to 3 in this case. And so if we reciprocate it to get it nicer, so like it'll be, if you reciprocate that one, it'll be 1 minus v squared over c squared, which will be 1/3. And then if you square both sides to get rid of that square root, you'll get 1/9 here. Yep. And so what else? So if you bring that v squared over c squared, so v squared over c squared, that way it'll be equal to 8/9. And so multiply both sides by c squared, so we get v squared equals 8c squared over 9 and 9, and we take the square root of both sides to get velocity. And that should give us our velocity. Yeah, so our velocity is equal, let me write it over here. So c squared, which is 3.0 times 10 to the power of 8 squared over 9, which is 3.0 times 10 to the power of 8 squared divided by 9. So now we got, yep, so 8 times 3 to the power of 8 is being squared, which gives me wait, I didn't square root it, sorry. Yeah, yep, I didn't square root my calculator, so did I write that right? Times 10 to the power 8 square root, yep, and then we take the square root of it. That gives me 2.8 to blah blah blah. If we divide it by, it's like, yeah, it's just a big number, it's close to c, the value, and all we have to do is divide it by the value of c to get it in terms of multiple of c, which gives me 0.94 c. That's it. So it would have gave me, this is what it gave me. So it gave me this 2.82 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. So it gave me something like this, and I just divided it by the c value, and it gave me a multiple of c. And that's it, guys. I hope you guys enjoyed this video and learned something through it. Please make sure to like and subscribe and share this video with your friends, and make sure you take care of yourselves. Bye-bye.